When I say the word ceramics, what pops into your head? For most of us, it's probably a coffee mug, right? Or maybe the tiles on your floor. And yeah, you're not wrong, but that's kind of like saying transportation is just about skateboards. We're about to peel back the curtain on a hidden world of high-tech materials that power literally everything, from your car's engine to life-saving medical gear. Okay, let's get into it. Just look at these two things. On the left, you've got one of humanity's very first ways to write things down and make them last, a cuneiform tablet made of baked clay. And on the right, these intricate little components that are the absolute heart of modern electronics and sensors. Separated by thousands of years, what in the world could they possibly have in common? Well, they're both ceramics, and this just brilliantly shows the incredible journey these materials have been on. So, to make sense of this huge and fascinating world, we're going to need a map. Think of this as a journey, an exploration of modern materials, where each region we visit is a different family of ceramics, and each one has its own unique purpose, its own set of superpowers. And here's the legend for our map. See that box at the very top, application? That's the end goal, right? Whether it's a simple brick or a super complex sensor. But its function, what it does, is a direct result of what's going on underneath. Its microstructure, which itself comes from its basic atomic makeup. We're going to trace that path from the bottom up to really get why ceramics are the perfect choice for so many amazing jobs. Okay, first stop on our map, the land of structural ceramics. These are the real workhorses of the ceramic world. They're the materials you rely on every single day, probably without even realizing it. Their mission, their whole reason for being, is simple: be incredibly strong and unbelievably durable. So what's the core problem that these ceramics are here to solve? Well, it's one of the oldest engineering challenges there is, going all the way back to the dawn of civilization. How do you build stuff that doesn't crumble or break or just wear away? How do you build things to last? And the answer? It's baked right into the atomic structure of ceramics. First off, they have incredible compressive strength. That's just a fancy way of saying they're ridiculously hard to crush. The atoms are locked into this rigid structure with super strong bonds, which is why bricks and stone have been the foundation of architecture for centuries. That same atomic lockdown gives them extreme hardness. We're talking materials like alumina and silicon carbide that are so hard we use them to literally cut and grind steel. And finally, that means they're super wear resistant. Perfect for things like tough porcelain tiles on a busy floor, or even the tiny, tiny nozzle on a water jet cutter that blasts through solid metal. All right, let's leave the familiar world behind and travel to a much more extreme territory on our map: refractories. These are a very special class of ceramics, and they are designed for one thing: to survive in the most intense heat you can possibly imagine. I mean, just look at this. That ceramic bowl, a crucible, is pouring liquid metal. The temperature there would turn almost any other material into a puddle in an instant. This is the world refractories were born for. They are the true unsung heroes of every major industry that uses high heat, from making steel to producing glass. I love this line from the source material because it just nails it. A refractory isn't something totally different from a ceramic. Nope. They're the elite, the special forces of the ceramic family, specifically engineered to go into thermal combat and win. So the key thing to get here is that a refractory is a material that just flat out refuses to break down when you hit it with extreme heat, intense pressure, or even a chemical assault. It just holds its shape and stays strong when everything else fails. So anytime you see a furnace, a kiln, or an industrial crucible, you're looking at a refractory ceramic doing its job. All right, let's journey now into probably the most diverse and, honestly, often invisible part of our map: functional ceramics. Their job isn't just about being tough or handling heat. Nope. Their whole purpose is to perform a very specific electrical, magnetic, or even biological function. And this is where things get really, really cool. This table really shows you how a material's hidden talent connects directly to a gadget we use every day. So, take zirconia. It has this cool ability to conduct ions, which makes it perfect for the oxygen sensors in your car that help the engine run super efficiently. Then you've got barium titanate. It has a high dielectric constant, which really just means it can store a whole lot of electrical energy in a tiny space. That's what lets engineers build the microscopic capacitors that our phones and laptops need. And PZT? It has the piezoelectric effect. It literally changes shape when you apply electricity. That's the magic behind things like hyper-precise little motors and even some types of speakers. But functional means way more than just electronics. One of the most incredible functions is something called biocompatibility. A lot of these advanced ceramics are so stable and so inert that our own bodies just accept them. No rejection, no problems. And that has opened up a whole new world for medicine. And that means we can use ceramics for everything from dental implants that look and feel just like real teeth to the ultra-smooth, wear-proof ball and socket joints in a hip replacement. Even the tiny optical fibers in an endoscope, the ones that let a surgeon actually see inside your body, that's a form of ceramic glass. They are literally being used to repair and reveal the human body from the inside out. So we've seen what these amazing materials can do. But how does an engineer actually pick the right one for the job? It's a really complex decision, and it's all about understanding exactly what kind of threats the material is going to face during its life. Let's think about two really common threats. On the left, you've got thermal shock. That's what happens when a sudden temperature change makes a material crack. We've all seen this, like when a hot glass dish cracks when you put cold water in it. And on the right, you have chemical attack, where something corrosive, like an acid, just slowly eats away at the material. Now, to beat thermal shock, an engineer has a whole toolkit of properties they can play with. They could pick a ceramic with really low thermal expansion, so it doesn't try to change size too much when the temperature changes. Or they could go with one that has high thermal conductivity, which lets heat spread out quickly and evenly. They can even design in what's called porosity, basically tiny engineered gaps in the material that act like roadblocks to stop a crack from spreading. But if you're fighting a chemical attack, you need a totally different playbook. Here, the name of the game is creating an impenetrable fortress. The engineer is going to focus on things like making sure the glassy parts of the ceramic are super stable and ensuring it has really low permeability by getting rid of any little cracks or pores that a corrosive chemical could use to sneak inside. So, you see, it's really a game of trade-offs. The very thing that might make a ceramic tougher against cracks might also make it weaker against chemicals. The true art of ceramic engineering is exactly this, fine-tuning the material's internal structure, its microstructure, to find that perfect balance of properties it needs to survive whatever mission it's designed for. So, from the ancient clay tablets that recorded our first stories, all the way to the advanced composites that will shield our future spacecraft, ceramics are this quiet, incredibly powerful cornerstone of all human technology. They've been with us the whole time, constantly being reinvented to be stronger, smarter, and more capable. Which really just leaves you with one final huge thought. What seemingly impossible challenge are they going to help us solve next?